coming up next, we are going into generalized multiple tanks and applications for silicon-based RFmm wave IC. Now, radio frequency integrated circuits and wave IC play crucial roles in the modern wireless communication systems in laptops, smartphones, tablets, and more. But commercial silicon always faces issues of high substrate loss and metal loss. Therefore, a new methodology of multiple tank topology to cope with this loss issue has been proposed. This talk presents the proposed method and implementation from the fundamental concept and analysis to the new integrated circuits and system verification. And to elaborate on all of this is an awardee of the Chinese National Science Fund for Distinguished Young Scholars. He is also a fellow of China Institute of Electronics, a past associate editor, IEEE TMTT, and IEEE MTTS R10 coordinator. Ladies and gentlemen, let's welcome the Dean and Chair Professor of the School of Microelectronics of Tianjin University and the Director of Tianjin Key Laboratory of Imaging and Sensing Microelectronics, Professor Kaixue Ma.
Okay, thank you. Let me share the screen. Okay, can you see the screen?
Yes, we can see it really well.
Okay, let me start. Okay, thanks. Nice introduction from the presenters. It's my pleasure to be here and to give the talk presentation on the hardware design related wireless communication, for example, for Wi-Fi or short-range communication. And I take this opportunity to also to thank the invitation from the organization committee and also Professor Yu. And I think I just see the question from the Tony Quick about the what's the challenge, what's the issue brain if adopt from sub-6 GHz to terahertz. I think for the user end and for the base station, I think to adopt the very high frequency and a very high speed, the major issue bring to the hardware is the power consumption and also linearity. And there will bring a lot of challenges for hardware design, for IC design, as well as for the system integration. I think this topic will cover most of the issue we face from the circuit design and the system integrated level to see how we'll deal with this kind of a challenger problem. The topic of my presentation is generalized multiple tanks and applications for silicon-based RF and millimeter wave IC design. And I'm Kaixue Ma from School of Microelectronics at Tianjin University. And my presentation includes the following parts. First of all, I will give the background, and later on, then I will introduce the single tank versus the multiple tank, and we'll see how the advantage we can achieve by using this kind of multiple tank technologies. And we'll use the multiple tank technology for the VCU and frequency divider application, and also introduce this kind of multiple tanks for amplifier design and also switch application. And we also adopt this kind of multiple tank technologies for transceiver SoC, and we'll also give some insight for the future applications. And we'll also share some other related work of our team, for example, for the Wi-Fi short-range communication and for 5G millimeter wave SoC development in our team. And finally, I will give the conclusion. And for any wireless communication system, before we start design, we need to do the product definition. For example, we design a short range 60 GHz wireless communication, we need to, first of all, we need to consider the application scenarios. Based on the application scenarios, we can define, for example, the communication range and the coverage, power, operation, and also data rate. Of course, based on these kind of application scenarios, we also have the confinement of the front end. For example, the TXX power consumptions, the maximum bandwidth, channel and phase noise, linearity, and the severity of the spectrum as well. Of course, for the commercial application, we also need to consider the temperature range. For example, we need to cover minus 85 degrees to plus minus 40 degrees to plus 85 degrees. So this application environment requirement, of course, based on application scenarios, we also, from the user end, we need to have the baseband, which helps to define the I/O interface and the power constraints, and also modulation schemes. Of course, we also need to define the access schemes, delay constraint, especially for high-speed communication system. The latency has become a very important issue for 5G and also for 6G. Of course, we also need to have the ad hoc constraints. So by this kind of requirement, we also need to have the MAC and file layer definition. For example, ADC-DAC, we need which kind of a data rates to support this kind of communication range. I think these general pictures can give us an insight for any wireless communication system. What's the major issue we need to consider for our system design during our design? Of course, for this kind of wireless communication system, the overall constraints is this kind of IC chipset or this kind of solution. Does this cost matching to the application scenarios? This is very important, whether the market can accept or not this kind of the chipsets or the system. For our 60 gig design, we actually our targeted portable segments, which is in the range below 3 meters. And we support Type 3 and Type 4 mobile device use only single carrier modulation to save the power and the maximum bit rate to 2.5 gigabit per second. And of course, there's other applications for short range communication, and there's also other applications. I think this is based on the IEEE 802.11ad standards. During the time, the standard ongoing, and we carry on a lot of fundamental research for this kind of application. So for the portable device, the major consideration is the system has to have a battery efficiency. We need to have the circuit and the system have a low power consumption. Of course, for system, we need to have a low loss as well, and also the size, which are crucial for the cost effective and also application. So the size is become very important for the IC design. So which kind of process we can select for the short range communication system? We do have a investigation. Right now, for the millimeter wave design, there are a lot of applications during the past several decades. It's actually based on the gallium arsenide 3-5 groups semiconductor process. But the commercial silicon is actually the most of the cost-effective way for mass production. And right now, the silicon-based IC dominates the IC market, about 90% of the total IC. So, which is widely used in the digital, analog, and sensor, and also RF and the millimeter wave in recent years. And it's also, for example, this widely used in the computer, smartphone, automobile, and also some space applications. Here we show the examples for the smartphone, which use a lot of low cost and low power, small size chipsets in the phone. So the overall power consumption and the cost become major issue for the portable device. So for the commercial silicon, we do have a number of process to be a good candidate. For example, CMOS process, or silicon germanium by CMOS process or SOI process. Here we show the typical multiple layers silicon process. We can have a cut view of the process. This process of single poly 6 metal layers process, we can see there's a six metal layers from metal 1 to metal 6. So these metal layers we can fully utilize for the passive, for example, inductors, capacitors, or the interconnect applications for our IC chipset design. Besides the active device like the MOSFET or the diode, all these kind of active devices. So for this kind of commercial CMOS process, so for the silicon germanium, what advantage for the silicon germanium, which is also the one good candidate, because right now most of the process I think is based on 6-inch wafers, but CMOS the dominance is based on the 12-inch process. So for the very large volume, the CMOS process become a very good candidate. Of course, the SOI process right now also have a 12-inch process, but the silicon, they use a high resistivity silicon and also have the silicon oxide box layers to reduce substrate loss. So for our consideration, we choose the silicon germanium for our IC design, but we also still face the same challenges. So for this kind of multiple layers, metal layers, we have a very good advantage, very good advantages for high level integration. We can build multi-layers, inductors, passive device to shrink the size, but we also face challenges because we use a commercial silicon, which have the low substrate resistivities, normally about 10 ohm per square. So this compared to the high frequency, for example, millimeter wave design, like the Rogers substrate, the resistivity as high as up to 10⁻⁷ ohm per square meter. So this brings a lot of challenges for our IC design, especially at the millimeter wave frequency band. The substrate loss become a dominant issues, and beyond the substrate loss, another issue is the mental loss, because there's an ohm loss that generates. And let's see how the substrate loss affect our IC design at the millimeter frequency band. Here we show some paper with publication to demonstrate if with a low silicon substrate, 10 ohm per square, and without, we can see with this kind of ohm loss, substrate loss. So the insertion loss can be up to 10 dB. That means there's a 90% of energy is become a heat sucked by the substrate. So, and this kind of heat also become as a noise for our active circuits as well. So, so this kind of substrate loss become a major issue for our IC design. For example, here we show the bandpass filter design. The loss up to 8 to 10 dB is become a challenge for the filter design. And of course, this kind of filter also demonstrate as a passive device. If we use it for inductors or other passive elements, the mental loss and the substrate loss still have same issues for our IC design. So from this kind of investigation, we will become have this kind of our project motivations. So we see the high substrate loss and mental loss of commercial silicons. What's the issue caused by using this kind of high loss substrates? So the issue caused for RF and millimeter wave silicon-based IC circuit design will first of all will have a low quality factor for resonator or LC tanks, because this kind of resonator or LC tank is widely used in the filter, oscillator, and other matching network as well. So the second issue bring for this kind of disadvantages is a large insertion loss for the filter and the switch. If we build the switch, use this kind of passive, this kind of transmission line, use a high loss substrates, their insertion loss will become very large as well. And also this kind of insertion loss will become a power issue. They will have a large power consumption and low efficiency for amplifier. And we use for the low noise amplifiers, we'll have more noise figure for our low noise amplifier as well. And then we use this kind of issues for other passive circuit design, the loss also become an issue. And for the source signal generators or voltage controlled oscillator, and also frequency divider and synthesizer, the poor phase noise due to this kind of high substrate loss and mental loss will also bring to our design system. Based on this kind of investigation, we propose solution for the multiple tank-based circuit and topologies to improve or enhance the circuit performance. So before we start, let's choose a single tank as contrast to the multiple tank. Here we show the single tank is formed by a inductor and capacitors and also the equivalent resistance. This have become a symbol for the equivalent circuits. We can do a simple analysis for this kind of LC networks will behave as a resonator or LC tank. So it will resonate at the resonance frequency. So below the resonance frequency Fx is behave as capacitive behaviors, and above the resonance frequency it behave as an inductive response. So for the tank qualifiers of this kind of LC tank or resonators will define as Q is given by this kind of equations. Is R divided by the also inductance based on this kind of equation. And after simplification, we can see the qualifier is related to the equivalent resistivity and also with capacitance and inductance. So we can also do a simplification. The LC tank qualifier will be determined by parallel connections of the inductor qualifier and the capacitor qualifiers. So the maximum value will be determined by the minimum value of the qualifier, either inductor or capacitor. So this roughly discussed about the single tank. For the single tank, there's we can see we build this kind of LC tanks. We use a silicon substrate. We will use the inductors. The spiral inductors we build on the silicon wafers. So the inductor, the Q will reflect the energy store over the energy dissipation. It will defined by the integration of this kind of equations based on the EM field. So the overall qualifier will give in this kind of equations, which counter in the silicon resistivities and also the parasitic capacitance of silicon oxide. So dominant loss for this kind of cheap LC tanks is from the inductors for the RFIC design. And the inductor have also the electron loss and the magnetic loss. But the parasitic electron loss is dominant for this kind of inductors, because the silicon the commercial silicon, the magnetic loss factor is can be negligible. So this is a major consideration. Based on this kind of understanding, we form this kind of dual tank circuit to illustrate our concept. So here we have the first resonator, which actually are LC tanks, and we have a second LC tanks. We want to put these two resonator or LC tank as closer as possible to make them copying each other. Between these two resonator or LC tanks, you will have the magnetic coupling and also the electrical coupling. So this coupling coefficient can be defined by the EMF field of these equations. This Km defines the magnetic coupling efficiency, and the Ke defines the electric coupling coefficients. And we put this to LC tank or resonator as close as possible, which will be equivalent to a equivalent resonator or equivalent LC tank. We do the analysis based on simplified second model. We do the analysis. The quality factor with respect of the A and B to LC tanks based on the K equal to 0.5 and K equal to 1. The quality factor is dramatically improves due to enhance the magnetic coupling. That means most energy actually storage in the transformer due to the magnetic coupling. So we generalize this kind of dual tank to the multiple tank. We have this kind of sector matrix. We can see this LC tank from LC tank 1 to LC tank N. This LC tank will be mutual coupling based on magnetic mutual coupling together. We can derive the matrix, coupling matrix based on the Kirchhoff laws. We generate this kind of matrix. We solve this kind of equations. We get the two resonator frequency based on the single port network analysis. We can see the first operation frequency, resonator frequency, is actually almost omega 1. It's related with the tank number N and also the LC tank values, the value, inductor value, and the capacitance value. And if K equal to 1, we can simplify the equation, become Q1 equal to this one. Based on this kind of equation, we can get this kind of insights. There were two frequencies. These two frequencies can be adjustable either by inductance value or capacitance value, and also the tank number, and also can be adjusted by the coupling coefficient K. And the second insight we can draw is can form two or multiple networks, and the quality factors is related to the tank number N. So we do the analysis based on the circuits, and we can see we can increase the tank number from 2 to N. Actually, the operating frequency as the first resonant frequency actually shift to the low frequency, and also that means if we shift to low frequency, that means the circuit size can be shrink, can be reduced. And the second thing we can see with increase of tank number based on the coupling coefficient equal to 0.5, we can see the quality factor is also dramatically enhanced. So the equivalence LC tank quality factor actually enhanced. So based on this kind of advantages, apply the US patents, coupling multiple tank circuits based on the US patent. And here below, in the following parts, I will give the introduction of how we use this kind of multiple tank concept and the topologies into our circuit design. First of all, I will give some design examples used for the water control oscillator and also the frequency divider application. And both this kind of VCU and frequency divider are the key building blocks in the accurate RF microwave source or synthesizer. And all exist in all the RF microwave transceiver for smartphone or equipment. So let's see the examples. First of all, we apply this kind of concept into the VCU design. we designed based on the triple tank concept for the VCU design. We can see when let the K copy coefficient, K equal to 1, the quality factor can be enhanced to 2 times compared to the fundamental LC tank. And if we, based on the tree tank, can be even further enhanced. So based on this kind of design, we can dramatically enhance the quality factor. And due to the quality factor enhancement, based on the Lissing equations, the phase noise of the VCU also improved significantly. And we also do the publication in IWFC conference based on these kind of ideas. And we also build this kind of circuits which can be seen the VCU have based on triple tank, have a very low power consumption, just the DC power about 9.8 milliwatts, and the output power up to minus 3.1 dB. And the frequency coverage have a very broadened frequency coverage because we use a multiple tank. Each tank can be adjusted based on step by step and based on digital control. So we can broaden the frequency operation range as well. And here we also compare our design with the state of the art. We can see the frequency tuning range can be up to from the 23 gigahertz up to 26 gigahertz. And the figure merit we achieved up to 185 this kind of performance. So the overall advantage we achieve by using this kind of multiple tank techniques for the VCU design, we achieved a wide tuning range and a good phase noise and the best power added efficiency. That means the energy saving schemes by using this kind of topologies and also low power design. And we also use this kind of concept for the inject lock frequency divider design. So this based on similar ideas, similar concepts, use a multiple tank as resonators for the frequency inject divider. So we also broaden the frequency range to cover from 21.4 to 25.1 gigahertz. And output power we have minus 2.5 dBm, and the DC power consumption is 5.8 dBm. And we also do investigation recently, as I think there's we also divide the dual tank injection frequency divider, which we do a good compromise between the phase noise, locking range, and the power efficiency, and also the chip error by using this kind of multiple tank. Because this kind of multiple tank, we can build based on the multiple mental layers. For example, we illustrate the 6 mental layers. We can fully use this system. The circuit size can be reduced by design use a 6 mental layer. We increase the actually vertical integration to reduce the surface areas of the total chip areas. And the circuit design becomes 3D design to shrink the size. This is a major trade-off. And we also use this kind of idea to build the dual tank, the triple tank, wider tuning range voltage oscillator design, VCU design, which cover frequency from 55.7 to 66 gigahertz, which have very good performance, and the chip error is only 0.347 millimeter square. And you can see the size here is actually reduced. The total size is actually reduced. And the design concept is we use a dual core concept and a triple tank. And the first tank use a Gerber cell as a negative resistance for the oscillator. And the second core 2, and also this core 1 and core 2 are coupling together based on the magnetic coupling. And the third tank which actually use a transistor together with the inductors to behave as a third tank. The third tank will collect the output power of first tank or second tank. And the operation will in this kind of manners. We have the during the first tank operation, the second tank will be off. And to save the power, during the signal call off, the tank is still there to enhance the first call oscillator LC tanks. So by doing so, we let the first call to cover the low frequency band, and let the signal call to cover the high frequency band. By doing so, we can have a very broadened, double the frequency tuning range, while the phase noise enhanced and also the tank color factor enhanced. This advantage we can achieve by using this kind of tricky design, use a multiple tank. And here we show the design implementation and examples here. We use a dual core. We have a wide tuning range and a good phase noise, and no need buffer circuit, because as we know, when we do CMOS circuit design, the buffer circuit normally draw a lot of power. We use a transformer to replace the active buffer circuit to save the power. So the overall chip error reduced and the power also be reduced. And we also do investigation about this kind of multiple tank used by other research. Here's some examples from the other groups. We use they use this kind of properties for the circuit design. They also achieve very high frequency, 73.8 gigahertz, and the tuning range up to 41.1, and also have very good phase noise. And this is also based on the multiple tank set to finish the design. They are, based on their comments, they actually use a magnetic tuning much more and achieve ultra wide frequency tuning range. And this from other research group, Zhihua Wang's group, they also use this kind of multiple tank concept to design the VCU, which operate at 59.3 gigahertz tuning range, 38%. And the DC power consumption also very low, 8.9 to 10.4 milliwatts. And the chip error, it actually is also reduced significantly. So from this kind of example, we can see the tuning range is a wide band without degrading the resonator's quality factor by using the even mode or odd mode tuning. And here's the other groups use this kind of multiple tank concept for the second harmonic impedance control to enhance phase noise performance, and as well as in the frequency tuning range. Due to the time limitation, I will not give more detail about the design. But we can clearly see this kind of concept actually reduces the phase noise and enhance the performance. And here's some examples. You can see the chip error is also very small. And this some other design use this kind of multiple tank. Here is actually triple tank, triplet coupling tank from the Wei Hong's groups. They designed the wide tuning range frequency control oscillator, which also have very good performance and design. And this from the other groups for the class F type VCU design use multiple tank concept. And I think based on this investigation, we can see this kind of multiple tank technologies is now widely using the VCU design to achieve very good phase noise and also the performance. These other groups, K-counts for groups, we use a triple tank to enhance the circuit performance as well. And these are some other design for the terahertz VCU. The omnium frequency up to 239 gigahertz for very high frequency use a multiple tank concept to finish design. And this another example for the 150 gigahertz to 190 gigahertz VCU design. From this kind of thing, we can see now this kind of technologies become very popular for the RFIC design for high performance. And we also use this kind of multiple tank concept for the amplifier design, because RF millimeter amplifier is a key building block for in RF millimeter system design, especially for the transceiver and other type applications. Here we build some amplifiers use a multiple tank concept. We design the power amplifier, which based on the 65 nanometer CMOS process, which have the gain of 26.6 dB and output consumption output of 19.7 dBm. Use a CMOS process and very broad bandwidth. Here we show the performance. We can see from the design, we can see we have very broad bandwidth and also the very small chip errors, and the power efficiency is very good based on compared with the state of the art. And we also use this kind of concept to design the reconfigurable amplifier based on silicon germanium by CMOS process. Use a dual tank to fine tune the optimal frequency as well as the matching load. By doing so, we can achieve very good power adding efficiency of 55.9% of PAE. And the gain can be variable from 1.8 dB to 6 dB. And the frequency coverage can be from 24.3 gigahertz to 35 gigahertz by using this kind of multiple tank concept. And we also use this kind of concept for the low-loss switch design. Here we show some examples for the 60 transceiver design topologies. They use either you can choose dual antenna schemes, which might need a filter and antenna and a power amplifier as well. And also you can use a TDD scheme. That means you might need the SPDT and also the filter for the design. For our design, we proposed the SPDT filters. That means the switch behave also as a filter during the operation. So we do this kind of combined design. We do a comparison between the state of for the switch. The minimum loss based on investigation is about 3.5 dB at millimeter frequency band. And for the filter performance, here we have a table. The loss actually based on scheme. This second scheme, the traditional way second scheme, the overall loss, the filter plus switch, the loss is actually around 6.4 dB to 9.3 dB. But based on our proposed filter switch scheme, actually we can achieve the low incident loss about only 3.2 dB. Here we show the design example. We first of all use this kind of multiple tank to build the SPST single pole single through switch. We can see the incident loss is only 1.8 dB, 9 dB. And they also use this kind of multiple tank to build the SPDT. We can see the incident loss only 3.2 dB. And the isolation at 60 gigahertz about 20 dB. And the switching on off time is very short. And it's only 0.18 nanometer. And the additional benefit we achieved actually is the power handling, because we use a multiple tank. Each tank will separate the storing the energy. That is overall the power P1 dB and it also increased by increase of a number of the tank. So we will have very high P1 dB, more than 21 dBm, because due to the limitation of the test equipment cannot get the exact value. And the key feature we can achieve by using this kind of multiple tank for the filter switch design, we achieve the compact size, low incident loss, and high P1 dB and power handling capability. And we also use this kind of concept for the terahertz frequency IC design. Due to the time limitation, I will not go through the details and just a brief shows the results. By this one, also you use internal tank to control the coupling coefficiency, and to fine tune of the matching as well. Here's the analysis based on triple tank concept for the circuit design. We can see the small iron reflector short port 3 to the ground to saving the power while enhance the factor. And here we compare when the coupling coefficient change, how the operating frequency band got affected, and also the performance, the S21 as a transmission performance got affected. And we also form actually form a second order bandpass response. Here we'll also do the analysis based on the switch on or off conditions. And then here we do a comparison based on the scheme 1A and scheme B. And we have a very small chip error, just 0.035, and actually size reduced by 90% of the circuits. And then here we show the merged performance for the 140 to 180 gigahertz. The internal loss only 3.3 dB, and also isolation can be enhanced by using this kind of auxiliary coupling lines. And here also we measure the return loss and also the threading time. The threading time is very short, within the nanosecond. And here also compare our design with the set-ups. We can see we saving the power, chip error by 90% for our design. And here's other design for the terahertz range. And we also use for the transceiver design by using this kind of multiple tank concept. We build this kind of dual chip transceiver, dual chip solutions for 60 gigahertz short range wireless communication. We built this transceiver chipset based on silicon jamming by CMOS process, and the baseband chipset based on the 65 nanometer CMOS process. This 60 gigahertz transceiver SoC, and this is a demo board, and the packaging, and also temperature packaging with the antenna. It's actually AIP streams we build in these kind of systems. And here we show based on this kind of transceiver chipset, we can support 4 gigabit per second based on EVM about 9.8 dBm per second. And we also show some demonstration. We can do a communication distance about 10 meters to do the video broadcasting from one end to the other end. And we also build the synthesize by using this kind of multiple tank concept, which have very good performance and a very small chip error as well. And for this kind of scheme, also used for the other building blocks, transceiver building block applications. And for future applications, this kind of multiple can form, using this kind of multiple tank schemes can form multiple port silicon system applications. And also can be used as a low loss matching networks for the circuit matching applications, and can be used for the high power combination scheme using multiple tank, and it can also be used for the energy harvesting applications, and can be used for the other off-chip applications. So for this kind of multiple tanks, the key feature or key advantage we can achieve is a low loss, high Hall factors, and compact size. And below, I will show some our related work for our team. Because our team right now builds the RFIC design, which cover from 300 megahertz to terahertz frequency range. We do a lot of investigation and research on the silicon CMOS, BiCMOS, and CMOS SOI silicon oxide CMOS process. And we also build a lot of IC for 3.5 gallium arsenide MMIC design. And we also start from IC to the whole package design to finish the whole design chain. And we also proposed new design scheme for 3D integrated platform, which calls the substrate integrated suspended line technologies for circuit design. We actually do a lot of research and a lot of publication based on this kind of seesaw platform. And right now we also do a lot for the 5G millimeter wave application. Here we right now we finished some design of a 28 gigahertz transceiver for this kind of base stations, and we also build some phase area front end use a BiCMOS process for the for this kind of beamform 5G base stations. And we also do some innovation design for the dual band transceiver chipset, which have the dual mode operation, which we can have the 28 gigahertz mode or 39 gigahertz mode. That means a single chip can support dual band operation. That means you will have an even better application for this kind of chipset. So this kind of dual chipset, we actually integrated the dual band LNA, ultra-band mixers, and also the sensor size, which become a fully integrated SoC for 5G applications. And here's the performance for the TX mode, the overall gain and the performance. And this for the receiver mode conditions, we can see we have very good gain and gain flatness. And also build some by use CMOS process, use some high resolution phase shifter design. And we can see we cover actually 30 to 36 gigahertz and very small chip area, but we have very good phase resolution, and we can cover from 360 degrees, and with RMS very small. And here's a measurement result for the amplitude error smaller than 0.2 dB and the phase error smaller than 1.3 degrees. And we also built some a new FEM for the next generation Wi-Fi applications at the IWFC 8.11ax standards. And for these kind of applications, the major issue is how you design the very low noise and very high power efficiency. Especially you need a counter in the very high linearity, because we need for this kind of Wi-Fi 6, you need a support very high order modulation, 1024 QAM modulation, which have a very high linearity requirement than the Wi-Fi 5 or Wi-Fi 4. And here some example, we use a gallium arsenide to build the power amplifier, and we also use a SOI process to build the LNA low loss amplifiers. And with this one, I will draw my conclusions. And the new methodologies of multiple tank topologies is proposed to elevate the substrate loss issue for commercial silicon. And the application in new circuit like VCU divider and amplifier switch are verified the advantage of the proposed method. The techniques are adopted in 6 transceiver SoC, and the other related work of our team on 5G millimeter wave and sub 6 GHz application also introduced. And we also support by our lab facility. We have a very good test equipment which can cover from 100 megahertz to 140 gigahertz, 1.14 terahertz proper station system, and also the oscilloscopes and VNS. All these kind of facility will support our IC design and development. And with this one, I will end my presentation. Here's big pictures of my campus, the Tianjin University, which is the first modern university of China, located in Tianjin. And very nice pictures is the top picture is from our old campus, and the below is the new campus. We also have a lot of faculty position opening worldwide to get the good talent for the teaching and the research in Tianjin University. Welcome. Thank you.
Thank you so much, Professor Kaixue Ma. And of course, that was a really great presentation. And we've got some questions for you. So we're going to move straight on to the Q&A, starting with this one. Can you explain the pros and cons in the multiple tank techniques for IC design used in low frequency and high frequency? Would you be able to elaborate on that?
Okay, because this kind of multiple tank, we can use for low frequency as examples shown in the presentation. For the low frequency, we can use a multiple layers to dramatically shrink the circuit size, because we know the circuit size is related with the wavelengths. Because at low frequencies, the wavelength is larger, and if we use a multiple tank, which can be vertically integrate the multiple tank to shrink the size of the overall chip areas, and also the tank, the quality factor also enhanced. But for the low frequency, I think there's a major, we have a lot of advantages. There's almost no disadvantages. Of course, maybe the disadvantage maybe is the design complex. We cannot, because the design will take a lot of time to make sure the design can fit your expectation. And for the millimeter wave frequency, because the circuit size becomes smaller, if you use a passive element, for example, inductor or tanks, the size is shrink. We cannot use a very high tank numbers. For example, we can use a 2 tank or 3 tank, but we cannot use a 5 tank due to the size too small to for the layouts, the trace-through routing. They will have the wavelength limitation for very high frequency. Yeah,
Thank you so much for that answer. We have another question. This time it's from Diana R. And Diana R says, what type of modulation have you used for transceiver design, and how is it verified?
Okay, actually for our design, we do have several different types of RF transceiver design. For 60 GHz transceiver design, we actually merged the 60 QAM modulation scheme measurements, which can support actually 4 gigabits per second. And for the some power amplifier design, we actually use a 256 QAM modulation scheme to do the measurements. We actually use oscilloscopes to test the constellations and also the EVM to verify the linearity and the efficiency. And for our new recent research for the Wi-Fi 6 applications, we actually test based on IWFC standards, IWFC 80.11x standards, which were classified from MCX 0 to MCX 7. We based on standard to measure the performance to test the linearity and the output power specification to make sure it fits the application. Thanks.
Thank you so much, Professor Ma. We have another question over here, this time from Brinda S. And the question is, how can deep learning techniques play an important role in beamforming? Please explain.
Okay. Actually, the beamforming is because we majorly use for the hardware design, but for the beamforming, I think there are several ways. There are 2 ways. Actually, there are 3 ways. First way is use the analog beamforming, and the second way is the digital beamforming, and the third way is combine the analog and the digital beamforming. Because for the system applications, especially for 5G or 6G application, we will have a lot of transceiver front end. So the power consumption and the size and the cost become major issues. So we need to do a good trade-off between the cost and the beamform, the element numbers. So for the artificial intelligence, it's very good technologies to use the beamform, because if we use for the MIMO applications, we need automatically turn on or turn off certain channel or certain transceivers to save the power. And we also need to have very good coverage to make sure the user can be linked by using this kind of MIMO systems. So artificial, this kind of technologies will become a very good baseband solution to support this kind of beamforming to have a better power efficiency and even better coverage and better user experience. Thanks.
Wonderful. Here's another question, Prof. What are your comments on the application of wave for 5G application, and why do you design the dual band transceiver for 5G wave?
Okay, because right now the 5G worldwide, they have a different frequency band. For example, we have a 28 gigahertz to 8 gigahertz and 39 8 gigahertz, 39 gigahertz. There's two frequency band. The right now solution is they have the 28 gigahertz transceiver as one chipset and the 39 gigahertz transceiver as another chipset. And these two chipsets become a standalone chipset. Because if we use a single band transceiver, single band is the traditional ways, that means just a single transceiver can be only used one application scenarios. For example, 28 gigahertz transceiver can only use it for the 28 gigahertz application scenarios, and the 39 used for the 39 gigahertz transceiver application scenarios. But for our proposed solutions, we can cover the dual band 28 gigahertz plus 39 gigahertz. So for this kind of chipset, we actually the chipset error, chip error not increased, but the chip can be used for two applications. For example, for 28, we use the same chipset, dual band chipset. For 39, we also use a dual band chipset. By doing so we have one chip have more application scenarios. That means you will have more user to use this kind of chipset. This is my design concept. Yeah.
Great. Thank you for sharing that with us. And the questions continue to come in. This next question is: higher level QAM and OFDM need more RF backoff for linearity. How do you overcome this challenge to achieve good power efficiency for the power amplifier?
I think it's a very good question, because right now we move from 4G to 5G, even to 6G. What's the major issues we faced is actually the bandwidth. We actually have a very broad bandwidth. This bring a lot of challenges for our circuit design. And then another challenges is band use efficiency. We use a high order modulation schemes, for example, 1024 modulation schemes. So for this kind of high order modulations, the system linearity requirements become very stringent. These are two challenges we faced for 5G and 6G applications. So normally for the power amplifier, of course, for the whole transceiver design, we all needed to consider the linearity issues to do a good trade-off. The most dominant thing is about the power amplifier, the final stage of power amplifier. Normally we need a bank of 6 dB, even 9 dB, even 12 dB to have even better linearity. That means we actually bank off the design, because actually the power amplifier itself have out power capability up to, for example, 33 dBm, but we actually use during the application, we only use at 23 dBm, which we bank off 10 dB. That means your power efficiency will drop. So this issue we faced. How we deal with these kind of challenges? We need to find the new design ways. For example, we can use the Doherty schemes, new Doherty schemes, either the dual pass or three pass, to increase bank off efficiency, while at high power conditions, the power efficiency is still very good. This is a very good solution we needed to do. Of course, we have also have some new schemes. I use some new tolerances to even have a better power and efficiency. for bank of condition applications. I think in summary, I think we need to do a good trade-off to select the good topologies, new topologies, to have a good linearity. And also we need to have good bank of schemes, and also need to have some DPD scheme to increase the linearity while improve the linear out power. This is my answers. Thanks.
Thank you so much for that explanation. Our next question coming right up is this. What Wi-Fi IC and module do you build differently from the existing Wi-Fi?
I think I just brief, we do something right now ongoing. We just send for verification. I think we can have a better power efficiency and even under the bank of conditions. Because right now, the linearity, we need to meet the standard requirement from MCS 0 to MCS 11. There are some standard requirement based on IEEE 802.11x. So we need to meet the standard for the linearity and also other specification. But we need new schemes. For example, we use some current reuse or some different topologies to saving the power and increase the PAE for our chipsets. I think I don't have the picture to show here. They will just discuss based on some concept. This is the way we do it right now. Yeah.
Thank you so much, Professor Ma, for answering all those questions from our audience. And of course, a thank you to the audience for being so participative. We have 2 more speakers coming up later, so we look forward to more of your questions in the chat box and the Q&A tab as well. Once again, thank you, Professor Ma, for that in-depth look at generalized multiple tanks and applications for silicon-based RFmm wave IC. Thank you so much, Prof, for joining us from Tianjin.
Okay, thank you.